Okay, so in the last video we talked about diffraction, and in this video we're going to finish up topic 4.4, which has to do with the double slit experiment. Okay, and so the double slit experiment was an experiment designed by Thomas Young in the early 1800s, and basically the purpose of the experiment was to confirm whether or not light behaves as a wave or as a particle. And so this is something that had been debated for, hundreds of years, even going back to the time of Newton. Is light made of particles or is light a wave? Isaac Newton happened to think light was made of particles, and because he's Newton, a lot of people kind of went along with that just because he must know what he's talking about because he's a super genius in physics. But in the early 1800s, this guy Young did this experiment. And basically, this experiment was a really interesting way to confirm that light is a wave. And essentially how the experiment works is you pass light through two very small openings, and if light behaves as a wave, then you get an interference pattern. And if light behaves as a particle, then you don't. And it turned out that experimentally speaking, you saw an interference pattern when you looked at where the light was hitting. Okay, and so that kind of proved beyond a shadow of a doubt that light behaves as a wave. Now, if you did not see the original double slit experiment video, I'm going to link it here. If you did already see it, or if you want to see it again, that's up to you. Then you have an idea of how this experiment went. Now, I will just say one more thing, just to kind of have this in the back of your brain. In the 1800s, Young did this experiment which showed conclusive evidence that light is a wave. It turns out that a little over 100 years later, this guy named Albert Einstein won the Nobel Prize in Physics for what's called the photoelectric effect. And a lot of people think Einstein, won the Nobel Prize because of relativity or something like that, or E equals mc squared. No, technically speaking, his Nobel Prize was for the photoelectric effect, and he basically showed conclusively that light behaves as a particle. And so if you think about that, you might be saying, wait, didn't he just say that light is a wave? Well, it turns out light can actually behave as a wave or a particle, depending on what type of experiment you're doing. And we're not going to go down that rabbit hole because that starts to get kind of complicated, and you get into interesting parts of physics around the 1920s and 1930s, and that kind of leads to the development of what's called quantum mechanics. But we're not going to go down that road, other than to say that light is kind of an interesting type of thing. Okay, but for now, let's think of light as a wave. It is a wave in the sense that if you do the double slit experiment, it behaves like a wave would behave. Okay, so let's take a look at a diagram. And basically this is the setup of the double slit experiment. Okay, the typical diagram looks something like this. You have two very small openings, let's call them S1 and S2, and these are the double slits. When I say slit, I literally just mean like a really tiny hole. If you had like a really, really thin razor blade, you could make a hole that's really thin, and you pass light through it. Okay, you have some type of coherent light source coming in from the left side, going to the right, and they go through the two slits S1 and S2. And the wavelength of the light is lambda. And what happens is that the light is actually going to go through the two slits, and there's going to be some type of projection screen back here over here on the right side, where you can look at the pattern that emerges. Okay, so the lights travel through the slits, they diffract through each slit, so they spread out in circular patterns as they go through the two slits, and those waves interfere with each other and cause an interference pattern on the back screen. Okay, now, going back to the idea of the double slit experiment, you would suspect that if light is a particle, if you shoot a bunch of particles, imagine shooting like a bazillion BBs at two openings, then you would expect a pattern something like this. Okay, you would expect that the particles would go through and they would land right behind where the openings are. Okay, but if light behaves as a wave, then what would actually happen is as the waves travel through the openings, because waves experience diffraction, that is a wave behavior, then those waves would interfere with each other and you would get these bands, this interference pattern, where it alternates light, dark, where you have constructive and destructive interference alternating back and forth. Okay, and it turns out that's actually what you see if you do this experiment. Okay, and so because light, if you do this experiment with light, you get an interference pattern, and because interference is a wave behavior, that obviously implies that light acts as a wave. Ta-da, there you go. Okay, so good for Young for coming up with this experiment. And this is just kind of like a more complicated picture of the same type of situation, showing how if you have a light source coming in, it hits the two slits. This kind of shows you the actual, transverse waves in there, and then how you get this alternating pattern of bright spots and dark spots on the back screen. Okay, areas of constructive interference and destructive interference. The brightest spot is right smack in the middle between the two slits, which is kind of what you would expect. That's sometimes called the central fringe. And then going out from there on either side, it alternates. Wherever you see a dark spot, you have destructive interference, and a bright spot, you have constructive interference. And that just kind of, goes back and forth, because as you go back and forth along the screen, the path difference changes, which causes, either you have the conditions for constructive interference or destructive interference, depending on the path difference. Again, these are just more pictures of the same thing. This one on the left is obviously an animation. This one on the right looks to be like a real picture done with a laser pointer. Okay, and so you can kind of see how the brightest spot is in the middle, and how you have like dark spots in between these red dots. And they actually get farther apart as you go out, but there you're seeing the wave nature of light. Because every place you have a dark spot, you're having destructive interference. Now, just to kind of mess with you, I will also say that this type of experiment has not only been done with light, but it's actually been done with electrons. Okay. Yes, that is true. We have essentially done the double slit experiment with electrons. And if you're wondering how do you do the double slit experiment with the electrons, like electrons are so small, like where do you get two slits that small? Basically, they've done this experiment using the fact that atoms and molecules are really small, and so by shooting beams of electrons at crystals, the spacing between the atoms act as slits. And it turns out you actually get an interference pattern with electrons, okay, which would imply that electrons also behave with wave-like properties, which, if you think that's weird, it is. And so we're not going to get too far down that rabbit hole, because again, I don't want to blow your brains too much, but that is called wave-particle duality. It's a very interesting phenomenon. If you're interested in reading more about that, you can look up wave-particle duality. My understanding is they have even shot particles as big as buckyballs. If you've taken IB chemistry, you might know what a buckyball is. It's basically a carbon-60 atom, or a carbon-60 molecule. It looks like a giant soccer ball made of carbon atoms, and they've basically shown interference pattern with those giant molecules. Okay, and so even things that you think might be made of particles actually can exhibit wave behaviors, which is really kind of funky. Okay, so I'm going to link two videos in here. The first one kind of talks about the double slit experiment done with electrons a little bit, and then this is just a fun video where somebody created their own double slit setup at home using a laser pointer and some business cards. Okay, so as much fun as it is to talk about wave-particle duality, let's not go there. Let's talk about doing calculations with double slit problems. Okay, so we're not going to do anything too crazy, but you do have an equation given to you in the data booklet that's called the double slit equation. And here's basically what it looks like. Okay, the equation reads S equals lambda times capital D divided by lowercase d. Now, in this equation, S represents what's called the fringe separation. Okay, fringe separation is the vertical distance from the central fringe to the first maximum. Now, if you're like, what the heck does that mean? I'll show you a picture in a second so you get a better sense for what that is. Lambda is the symbol for wavelength. Capital D is basically in this picture, the distance between the two slits and the screen. You can see it's labeled down here. And then lowercase d is the spacing between the slits themselves. Now this is a very simple equation to use as long as you understand what everything in the equation represents, and as long as you pay close attention to the units. Okay, and the reason I say that is because S, lambda, D, and D are all in units of length, but they're not all necessarily going to be given to you in the same units. What I mean, for example, is wavelength of light is typically given in nanometers. D, the size of the slits, remember these are really, really tiny slits, and that's often given in centimeters or millimeters. Okay, and then capital D is usually given in meters. In order to do calculations with this equation, you have to make sure that you convert all of the units to the same thing. Okay, so if you have, millimeters, nanometers, and meters, then two of those you have to convert to meters to get an answer that makes sense. Now we'll do some examples in a second. I do want to point out that this equation is given to you in the data booklet. It's right here, but it's your responsibility for understanding what each term in the equation represents. Okay, remember capital D is the distance, the horizontal distance between the two slits and the screen. Lowercase d is the distance between the two slits themselves. And just to give you a visualization, take a look at this picture and you can kind of see what each thing represents. So notice here that S is basically the vertical distance between two bright spots. Okay, so the central fringe, that's that big bright spot right here in the middle. Okay, that's the central fringe. The first maximum next to that is up here or down here, and that separation is S. And so this equation allows you to calculate S, or actually practically speaking, what you would do with this equation is most likely you would use it to calculate the wavelength. This gives you a way to calculate wavelength of things like light, because practically speaking, you can measure D very easily. Okay, you can measure both D's very easily, and you can actually measure S easily as well, because you can just, project it on a screen, go up to the screen with like a ruler or something, and measure S. And so if you were actually using this equation in real life, you'd probably be using it to find the wavelength. And so if you ever wanted to know, like, how do we know, red light is 700 nanometers, well, we can do experiments like the double slit experiment to find the wavelength. Even though it's a very small value, we can take advantage of, interference and double slit experiment to do those types of calculations. Okay, that's just the same type of picture. So let's do an example. Okay, so this says coherent light having a wavelength of 675 nanometers is incident on an opaque card having two vertical slits separated by 1.25 millimeters. A screen is located 4.5 meters away from the card. And the question says, what is the distance between it should say the central maximum, and the first maximum? In other words, you're asking, what is S? Super easy calculation as long as you convert all of the units correctly. If we're solving for S, we're given the wavelength in nanometers, which means we need to convert to meters. Remember, nano is 10 to the minus 9. So here in the solution, you can see they multiply by 10 to the minus 9 to convert from nanometers to meters. Big D is given it in meters, and then little d, they multiply by 10 to the minus 3 to convert from millimeters to meters. But besides that, That's basically it. Okay, super easy equation to use with the double slit experiment. Couldn't be easier unless you forget to do unit conversion or unless you forget what one of the symbols represents. All right, now just to look at one more question, let's take a look at this. Blue laser light of wavelength 450 nanometers is shown on two slits that are 0.1 millimeters apart. How far apart are the fringes on a screen placed 5 meters away? Okay, so for this calculation, by fringes it means bright spots. And so we have S equals lambda times big D divided by lowercase d. Lambda here is in nanometers. I do want to point out that wavelength is measured in meters. A lot of people have the tendency to think, oh, okay, wavelength, I need to convert to nanometers. No, wavelength is supposed to be measured in meters. It just so happens that visible light has a wavelength in nanometers, and so it's very common to see wavelength given to you in nanometers. But there's nothing special about nanometers, other than the fact that light that humans have evolved to see happens to be somewhere in that wavelength. Okay, so that's why we're multiplying by 10 to the minus 9 to convert from nanometers to meters. Okay, meter is the unit for wavelength. Big D is the distance between the slits and the screen, which in this case is 5 meters. And then lowercase d, we have 0.1 millimeters, and milli is 10 to the minus 3. All right, and so this is very easy to do this calculation. I will tell you right now that some ways that they make these problems more difficult is sometimes they'll say something like, here's this information, the first bright spot and the third bright spot are this far apart, and they ask you to solve something. And so you do need to know that S is the distance between one bright spot and the next bright spot. Okay, and so sometimes you have situations where you have to like count bright spots and take that into effect. But aside from that, and aside from getting the units correct, these problems tend to not be very difficult at all. Okay, so I'm just typing this into my calculator. 450 times 10 to the minus 9, multiplied by 5, divided by 0.1 times 10 to the negative 3. I get S equals 0.0225 meters. And honestly, if you wanted to, you could write that in terms of centimeters or millimeters. I could say 2.25 centimeters, or I could say 22.5 millimeters. Since we're already in meters, this makes the most sense. But sometimes you'll see in the IB mark scheme, sometimes they'll write this in different units. Okay, just for simplicity. Now take a look at the second question though, because this is a more interesting question that they ask sometimes. If you replace the blue light with red light, would the fringes be closer together or farther apart? Okay, so think about this. What's the difference between red light and blue light? And what does that mean, fringes closer together or farther apart? See if you can answer this question. Okay, so red light has a longer wavelength than blue light. Also, when it's talking about the fringe separation, it's talking about S. So take a look at this equation here. If I were to increase lambda, keeping everything else the same, that means S would also increase. So because red light has a higher wavelength than blue light, the fringes would actually end up farther apart, because obviously if I multiply by a bigger number on top, I'm going to get a bigger number on the left side of the equation as well. Okay, and so here's what the answer key says for this problem. Okay, so try to do this calculation on your own. Let's see what you get. Okay, I will put the answer to that in the feedback. And that's basically it for 4.4. Okay, so we are done with wave behaviors. In the next video, we will start talking about standing waves. And remember, this unit covers 4.4 and 4.5, but most of the stuff is going to be under 4.4 because there's not a lot to standing waves, as you'll see. As always, please let me know if you have any questions, and I'll see you guys in the next video.